Welcome back, everyone, for the second part of this introduction to dilation surfaces. Okay, so, well, we'd left it to defining moduli spaces containing a dilation surface as this one. So we want to see how we can deform them and obtain some form of continuous manifold and parameter space of such objects. So maybe before doing that, I want to say a word about something that I sort of swept under the rug during the first part, is the shape of singular points. So maybe something that you will have noticed is that when you construct a dilation surface from a polygon like this, well, you have those vertices that project onto a point or several points on the surface, and at those points the affine structure, the dilation structure, cannot quite be extended, and there is an obstruction to that. So I just wanted to describe this obstruction to you. So the obstruction is the following. Basically, you start working with the plane and a half line, and you shear along the half line. You get something like this. So I've put a marker at the initial point before I shear. And what I do is I dilate or contract the upper part. In that case, I've chose dilating by a certain factor, and I glue back. So what I see is a global dilation. So my marker moves along the line, being dilated, and it gets bigger, and then I glue back. So it means that when I go around my singular points, well, in that sense, I sort of see a contraction. I would have followed maybe the circle of radius 1 of center this point, and I go around, and when I come back, I've sort of spiraled and contracted. If I go the other way around, I swell. So there it is. So now when I have such a singular point, because I could have done this construction on any angle of any angle, well, basically I have associated to such a singular point an angle and a dilation factor. And because I'm working with dilation surfaces where I'm gluing everything using affine maps which have a real linear part, I'm forced to have angles that are multipliers of 2 pi, multiple of 2 pi. So that's it for singular points. Hopefully you understand the structuring of those singular points. So now that we sort of know what those singular points should look like, we can define the moduli space. So the moduli space for a surface of fixed genus, a topological surface in a certain number of singular points, I can start by imposing a type of singularities. So each point I prescribe an angle that I can sort of record using an integer, such that the angle satisfies this formula, and a dilation factor around this singular point. So the only two restrictions is that the set of angles satisfy the standard Gauss-Bonnet formula, and that the product of those dilation factors counted taking account of the orientation is equal to 1. And once we've fixed a singular type, then I can define the set of dilation surfaces with that singular type. And as often when we define moduli spaces, we define them up to what I call a reasonable equivalence relation, meaning that 2 points are identified if there is a map from one to the other, there is an isomorphism, and that preserves the dilation structure. So maybe something I should say at this point is that when we have a dilation surface and we rotate it, we get a different surface, in the sense that it's important for us to know which direction on the surface is the horizontal one or vertical one, or we want to be able to talk of a given direction. And when you rotate a dilation surface, then you shuffle around the directions, and so you're not very sure which one is which. So a surface and its action under the group of rotations is a family of essentially different dilation surfaces. Okay, good. So this space is a nice analytic orbifold. It's not a complex manifold though, so it's a real analytic orbifold. It has a foliated structure that I don't want to discuss today, which is reminiscent of the structure on the leaves. The complex structure on the leaves is reminiscent of that of the standard moduli space of translation surfaces. And for our discussion, when we relate to the dynamical systems that we introduced in the first spot, it plays the role of parameter space. And that conjecture that we had on the structure of horizontal foliations becomes a conjecture on this parameter space for which we're using the natural Lebesgue measure, the class of the Lebesgue measure, induced by the structure of real analytic orbital. Okay. So this is just a little picture maybe to remind you of what we meant by Morse-Smale if you've already forgotten about this. So you have maybe finitely many cycles. By cycle we mean a closed orbit, closed leaf, like this one here. And maybe you've got a few more on the surface. And if you take any other leaf trajectory, then, it goes and accumulate in the future towards one of those, and in the past onto another one, etc. You have like maybe here you have your singular point that we just introduced. Okay. So before introducing the dynamics on the moduli spaces, there is one little thing that's it's not annoying, but makes the presentation a bit longer, and we'd like to move to the nice stuff. There are some dilation surfaces that are not triangulable, and you might wonder, but why are you saying this? And it'll have an importance a bit later. By triangulable, we mean that, and it's geodesic triangulation, so it's triangulation with a set of vertices is the set of singular points, and the edges are straight lines going from one vertex to another. And in the case of translation surfaces, you always have such triangulations, and it's not the case of for dilation surfaces. And well, the reason for that is actually quite simple. If you consider what's called the Hopf torus, which is the quotient of c minus 0 by dilation by lambda z, so maybe lambda is equal to 2, different from 1. That's the only thing that's important, which amounts to gluing two boundary circles of an analyst together using the only dilation that does that. Well, this cannot be triangulated for the stupid reason that you don't have a singular point. But even if you were to mark a point and decide this an artificial singular point, you couldn't do that. And the reason for that is because basically, to say very shortly, you have a cylinder of angle larger than pi. And so any potential edge of the triangulation would be forced to enter this cylinder, but because the angle's too wide, maybe an exercise that you can do at home, it will never come out. And Veitch showed this quite remarkable results that I'm going to tell you in a second. So yeah, maybe the thing my slide indicate that I should say at this point is that those triangulable surfaces survive small deformations, so they form an open set of the space of dilation surfaces, and that'll be an important point in the sequel. But yeah, important theorem of Veitch is that a dilation surfaces is triangulable if and only if it does not contain a large embedded cylinder. By large, we mean angle larger or equal to pi. Okay, so this is equivalent to the function that we introduced, so being strictly less than pi, the theta function. Okay, so in the sequel, we're mostly going to consider triangulable surfaces, actually only going to consider triangulable surfaces. So whenever now I'm talking about a moduli space, I'm actually thinking of triangulable dilation surfaces. So now I'm just going to tell you of a way to think of the geometry of D. So when I say geometry, maybe I think topology. It's not clear yet, but basically we have this function that we define, the theta, which to a dilation surface associates the angle, well, the largest angle of an embedded cylinder. And So now that we've restricted ourselves to triangulable surfaces, this function takes value in the open interval 0 pi, and somehow it tells us something about the geometry of our surface. If the surface has a very small theta, then it resembles a translation surface. A translation surface is theta equal to 0. And if, on the contrary, it's close to 2 pi, it has big cylinders which cover most directions. So you can see a lot of Morse-Smale stuff in that bit. So maybe the way I want you to think of it is that you have your moduli space like this, and it's swept out by this theta function. Close to 0, you have translation. I mean, at the infinity close to 0, you have translation surfaces. And when you move in this picture towards the left, you see wider and wider surfaces until you hit pi. And maybe you're not triangulable beyond that point, and you stop caring about what's happening there. But yes, and so there is a reason why I decided to draw it like this, with a very narrow end towards the 0 and a wider one towards the pi, and I'll explain that later. So now we're going to start discussing the natural dynamics on the moduli space. And maybe at this point I want to say a little word. So there is going to be a dynamical system acting on the moduli space, and we also have individual points of the moduli space which we think of as dynamical systems. So somehow what we're introducing is a dynamical system on the space of dynamical systems. And this, for people who like dynamical systems, I think I've said the word dynamical systems way too many times at this last minute, is what people are going to call a renormalization operator. Okay, so first thing to introduce is the SL2 action on this dilation surface moduli space. So if you know of translation surfaces, you already know what I'm talking about, but the group SL2 acts on polygons in the plane. And what we've seen is that dilation surfaces could be constructed using gluing together bunches of polygons. So you just take this action preserves parallelism. So if you take two parallel segments, the image of those two parallel segments by any element of SL2R are going to be parallel. So if I start from a translation surface, dilation surface, I apply an element of SL2R, I get something that I can also glue back to a different dilation surface. So it gets this nice action. And another important feature, if I want to be able to carry on that discussion, restricting myself to triangulable surfaces, is that it preserves triangulable surfaces only because it maps a nice triangulation onto a nice triangulation of the image surface. So I'm not going to linger too much on this SL2R action, although it's a very interesting action. I think there is this, to me, a very important question, is that the existence of a dense orbit, again, restricted to triangulable surfaces. And this question, I think, deserves attention, because somehow a positive answer to it would tell us that there is some form of universality in parametrized family of dilation surfaces. It says a lot about the real affine geometry of this surface. Anyway, I don't want to dwell on that too much. So within SL2R is a distinguished one parameter subgroup, which is the group of triangular diagonal matrices, and its action is often referred to as the Teichmüller flow, and that's what we're going to discuss now. This Teichmüller flow is the important tool that makes the link between the dynamics of foliations on individual surfaces with moduli spaces, and that's why it's very important. So for a second, I suggest we try and understand what this Teichmüller flow does to a surface, and more specifically, we're going to first have a look at what it does to a cylinder. So here I have a nice, fair cylinder, and it has the property that it contains the horizontal direction but doesn't, the vertical direction, but doesn't contain the horizontal one. So when you look at the action of a matrix of that form with a very, very large first coefficient and very, very small second coefficient, so what does it do? It dilates the first, the horizontal coordinates and contracts the vertical coordinates. So for instance, if you take that vector, well, you imagine that it's going to be pushed towards the horizontal one. And similarly, that one's going to be pushed towards the horizontal one, but towards the minus infinity a bit. So basically, you'd imagine that the image of this cylinder is going to transform to a cylinder with a much wider angle. And as t goes to infinity, well, you see that this sphere cylinder with an angle less than pi is going to be transformed into a cylinder with angle almost equal to pi. Okay, so basically this Teichmüller flow detects closed leaves, closed attracting leaves, that I call closed hyperbolic leaves. And if I have one in the vertical direction, so basically I have my dilation surface, I hit it with my Teichmüller flow and I wait for a very long time. If it had a hyperbolic leaf in the vertical direction, well, then what happens is that I shoot off to infinity in the sense that I had my moduli space here. I shoot off to the pi side of infinity. And where the angle, I mean, the theta function is equal to pi. Okay. And on the contrary, if my vertical foliation was anything, let's say minimal, but could have been like something more complicated, it's not clear what happens. And I mean, this is like a bit more subtle, and you'd have to, like, way more subtle, and it's not too clear what happened, but you could expect pretty much anything. It could be recurrence, it could go into the translation part, it could sort of drift off to the other bit of infinity, but at a much slower rate. So pretty much anything can happen. Okay. And that conjecture that we discussed earlier, in view of this criteria, the criterion that we've just given, the conjecture about every foliation, I mean, almost every vertical foliation being Morse-Smale, could be sort of rephrased in terms of the action of the Teichmüller flow. So you have this Teichmüller flow, and you want to say that almost every trajectory escapes to infinity in this wider path, whatever that is. Okay, and this, I think, for people who are used to hyperbolic geometry and geodesic flows, should remind them of the action of the geodesic flow in an infinite volume hyperbolic manifold. So I think an interesting research program would be to try and build a nice analogy between those dilation surfaces with their Teichmüller flows, analogy with a hyperbolic manifold with infinite volume and their geodesic flow. And why would you want to build such an analogy? Because in the hyperbolic case, we understand very well, and basically we have theorems already, so we'll come to that. But so just to give a picture of a hyperbolic surface of infinite volume, basically they look like this. Either you have cusps, and you probably know what a cusp is, or you have, and they have finite volume, the bits, that what they are, and you've got what people call funnels, which are those wider ends of infinite volume, which are essentially the quotient of the hyperbolic space by a hyperbolic isometry. So really, that really resembles what we've already seen. And if it were to resemble in a way that can be made more precise, then that would probably allow us to prove theorems, because in the case of infinite volume hyperbolic manifold, there is this very nice theorem of Ahlfors. So there is a hypothesis of geometrical finiteness that I don't really want to discuss, but for a large class of such hyperbolic manifolds, we know that trajectories of geodesic flow almost surely shoot off to the wide infinite paths, which is a statement that can sort of be rephrased in terms of the limit sets of the associated Klein group. So basically, I wanted to to end this discussion with a table that gives some more support to this analogy and what would be required to make everything work. But basically, a dilation structure is a point in the hyperbolic plane. Well, fair enough. So then we have the Teichmüller space, which would be the Teichmüller space of dilation surfaces, which would be the set of mod dilation surfaces, which would be equivalent to either the hyperbolic space or the unitary tangent bundle of the hyperbolic space. The mapping class group would be the Kleinian group associated to a Kleinian group associated to the discussion, the moduli space, the quotient of the hyperbolic space by this Kleinian group. Then you would have the bits for which the angle of a large cylinder is quite wide, correspond to the funnel, the wide N. When it's small, more towards the dilation, more toward the translation surfaces, look like a cusp. The Teichmüller flow, the geodesic flow, this Morse-Smale conjecture, the theorem of Ahlfors, and maybe I'll leave it on that note. There is an invariant measure for the action of the geodesic flow in hyperbolic geometry, which is what people call the Liouville measure, which is derived from the Haar measure of the isometric group of the hyperbolic space. And this measure is key in the analysis of the geodesic flow, and maybe in the case of dilation surfaces, we'd be very happy if we could find such an invariant measure, because it would allow for some transfer of technology between hyperbolic geometry and dilation surfaces. So I think I'll end there, and thank you very much for your attention.